Hi, in this video we'll be talking about containers in STL. So there are a lot of different type of containers that are available in STL. Something like sequence containers like vectors, list, TQs, associative containers like set and map, the unordered versions of the same, and some adapters on the sequence containers like queue, stack, priority queues and all. Okay, so we'd be looking into what these containers are and what are the operations they support and how you can use them in different scenarios. Okay, so first of all, vector. Okay, what's this vector? So it's just a dynamic sized array. So when we define integer arrays, we need to specify the size of the arrays, right? So if you want to keep the size of the array dynamic, we generally tend to use vectors. Okay, so the syntax for the declaration of a vector is something like this, that you have a vector of int a. This is the type of the vector, like each element will be of type int and the variable name is a, right? This is how you declare vector a of data type int. Similarly, if you want to use long longs, you use this, and you can define a size of the array by default as 100 in this fashion, and all of them will be zero initialized. Okay, so if you want to declare an int array of size n with elements initialized to 100, you can do something like this, that you just take in n, do scene n, then create vector int a of size n with values 100. Okay, and then you can print the last element, so a of n minus 1 will give you the last element in the array, right? So vector also supports pushback operation. Now what is this pushback? Given this vector, you can add an element to the end. Okay, that is what is pushback allows you to do in vectors. So in the implementation in the backend, what it does is keeps an array of size n, and if you push back something when the size fills up, it creates a double sized array and puts in the new element over there. Okay, so after n pushbacks, the elements are moved to at most 2n times, so there is an amortized cost of order 1, right? So n pushbacks, you will have 2n number of movement of elements, so it's order 1 per pushback. So you can call for the capacity of the vector if you want to, but this is not used. If you want to find the number of elements in a vector, you can use something called a dot size. Okay, so if you want to now traverse through arrays, so you can also declare arrays in this fashion, that 1 2 3 4 are the values, and then you have a sum equal to 0. You can just use a loop, I equal to 0, I is less than int of a dot size I plus plus, and you can keep on adding the values at the ith index in array. So you can access the vector's ith position in this fashion. Also you can keep size t, so this is a dynamic type. Also you can keep integer I equal to the last element, so a dot size minus 1 is the last element, and from that you go backwards. Also this also works. Okay, so in C beyond C++ 11 and onwards, you have this auto iterator, right? You can declare such kind of auto functions which support automatic data type detection for the x in when the code compiles, and it iterates through all the a. So this is a lambda iteration, and you can find out the sum of a whole array a in this simple code, right? There are also ways to use iterators. So iterators are like pointers on the containers. So just like in arrays you have pointers to memory locations, you in this case as well, you have iterators which move through the containers. Okay, so you can just declare iterator which is first equal to a dot begin. A dot begin is the first elements iterator, and it is not equal to a dot end. End is last plus 1th number of elements iterator, and it plus plus, you keep going forward, and you keep on adding the value at it. So star of it means value at it, right? Now also you can write it in this fashion. So these are all different ways to write traversals on arrays, right? So let's have a quick look on this portion of the code over here. So this is a bubble sort code where you take the array, write a bubble sort algorithm, and then print the array. Okay. Now there is something wrong in this code. Can you detect what? It's right over here. There is this a dot size -1, a dot size -I going on over here. Now why is this wrong? So if you look at a zero sized array, let's suppose this array is of size 0, and then if you call this, the output for this would be this. Now why is not -1? So a dot size returns 0, but the type of 0 is unsigned. Okay, so when you subtract 1 from unsigned, it becomes all ones. So it's not, there is no negative in case of data types which are unsigned, right? So everything becomes all 1 and it becomes a very large number. So in that way, this gives you some unsigned numbers and which are not relevant for you for the iteration, and this would be wrong if you write it. So it's a good practice to keep a dot size typecasted to integers, or you don't even subtract anything from a dot size. That's the best way you can code. Okay, so make sure you check these when you're coding, or else you might find bugs in your code, right? Now for vectors, dot begin and dot end returns the random access iterators for the first and the last +1 element, right? Now if we want to sort a particular array of vector, we just call sort a dot begin, a dot end, right? So the first and last +1, these are things that you pass and it gets sorted, right? Now there is a function called lower bound which finds you the first, the position of the first element which is greater than or equal to 2. Okay, for upper bound it finds out the first element which is greater than 10. Okay, the iterator to that position. Okay, and distance is a function in STL which gives you the distance between two iterators. It's like subtraction. So if you find out the a dot begins and it, so this gives you 1. Why? Because this is the element that it finds, position index I, right? That is the first element which is greater than or equal to 2 in this array. If you find out the element greater than 10, that's 6. So there are only 6 elements, so it's pointing out to this one because everything is less than 10, so less than or equal to 10, so it will obviously point to the end iterator, right? So you just don't directly print star of it2 if you had to print the element which is just greater than 10, because this might be the end iterator, right? So you always check first that whether the iterator that you're getting is end or not. Okay, and then you can use the iterator to get the value. Okay, so make sure you check these things when you're implementing iterators, or else you will get bugs. Okay, you can also create 2D vectors. So a vector can take a type, right? So you can also put in a vector inside a vector and declare such a 2D vector of size of dimensions n and m, and you can run a loop and take inputs into the arrays. So this works like the normal 2D arrays, but you're declaring it as a vector, right? Okay, so vectors can be compared directly using lexicographic rules. So these are some vectors that you have. So a is equal to b, a is greater than c. Why? Because this element and this element is same, this element and this element is same, but this element is less than this, right? So this will be false. Okay, so this is false. Okay, b is not equal to c. That's true because 1 2 3 and 1 2 4 is not same, right? A is less than d. So even though these two are same, if the size is less, we know that that comes first in lexicographic ordering, right? AB comes before ABC, even in case of strings. So if the size is less, in case everything matches till up to that minimum size, you get the smaller one to be before in the lexicographic ordering. Okay, now one thing you should know is, suppose you create a 2D array and you just run and fill in the values in 2D array. Okay, and you create some sort of loop which accesses that 2D array a lot of number of times, and you just print the number, right? So this is a code. Okay, now if you just want to create a 2D array, you can either create it in static format that we use in normal C++, or you can also use STL and declare it using vector of vector int, right? So which one should you prefer? Ideally, you should be preferring the simpler one, that is the static type, because they perform better than the STL, right? So keep this in mind in case you want to optimize on time, or if you're getting TLE on some problem and you're sure that the logic is correct. If you want to optimize, you can try to remove STL from your codes, because they are a bit more inefficient than the static versions of the code. Okay, so these direct normal arrays that we have in C++ are actually better in performance than the vectors that we create. However, this gives their own flexibility in, right, that you can resize and stuff. So you have to pay the price in some sense, right? Apart from vector, you have pair. So pair is like keeping two elements. Like let's suppose you want to keep elements something like this, 2 and 1, just two elements. So you can keep them in pairs. Okay. So pair is like a type template that is defined in utility header. So pair of t1 t2 is like two types, where where there are two data entries, first and second, and t1 should be the type of the first value and the t2 should be the type of the second value. Okay, so let's suppose you want to declare something like this. You want to keep so on and the value corresponding to that particular string in some pair. So you can create a pair and assign the first value to this and second value to this, right? So you create it keeping in mind the data types that would be used, and then you assign the values. Also, you can create it in one sentence using this syntax, right? Okay, so pairs can also be compared directly using the same logic as we did in case of vectors. So you first compare the first element. If they are same, you go to the second element, right? So you can just directly sort the arrays if you have pairs. Okay, and it will give you sorted by the names first, and then if it's same, then gives you sorted by the numbers. Okay, so in a lot of problems, if you want to change the ordering of the numbers, you can first of all like create pairs of some value and their index, and then sort the values, and you will get the other one in some particular ordering that you want. So this comes in handy in those cases. Apart from pairs, we have list. So list is a type that is implemented using bidirectional linked lists internally inside C++. So you have list of int of L with, let's say, value 10 and 20. You push back a value 30, so it will add 30 at the end. You can push at front, so it's like you have 10, 20, and it's a bidirectional linked list. Okay, so you add 30. You can even add 0 in the front. Okay, so these adding at the front and at the end, iterating from front and end, these are very standard operations in bidirectional linked list. Okay, so you can have an iterator to the begin element, and then you can keep on increasing the iterator. So it's first over here, then it goes to the 10, then it goes to 20. If you erase some particular iterator, so in bidirectional linked list, it's very easy to remove particular element, because we know that we just have to change the links, something like this. So deletion in bidirectional linked list takes order 1. Okay, so if you have some iterator and you want to insert an element inside the array or the linked list that you are maintaining, it takes order 1. Also, if you want to delete some element that you know iterator of, it takes order 1. So linked lists are helpful in these senses when you have to like dynamically remove elements and insert elements in between the array. Okay, so in those scenarios, you can refer to linked lists or bidirectional linked lists, and which are readily available to you in the list type that is available in STL. Okay, so you can traverse the linked list in the reverse direction as well. So we had begin and dot end, right? We also have r begin and r end. So it's like it just flips the direction of looping. So if you do a dot r begin and you run till it's not reverse end, you keep on increasing, so it will go from this end to this end. Okay, so it's like this is defined as r begin, and before this the element over here is defined as R end, okay, and this iterator moves in this direction, okay. Is this clear? Next we move to sorting a linked list, okay. So you cannot use sort L begin L end because L begin and L end are bidirectional iterator instead of random access iterator. Instead, linked list, bidirectional linked list can be sorted using merge sort algorithm, and this has been implemented internally in the C++ STL. So you can just call the dot sort function and it will sort the linked list, okay. So you should not be calling the standard sort function in these cases, as it does not work, because in doubly linked list, when you have the element and you have the pointers, when you have to go from this element or you have to access a particular element, you have to reach that from one of the ends, right? So if you have to reach some particular element, you will have to reach it from one of the ends and get its iterator. So moving through the list will take you on order n. So the standard sort does not work, but it has an inbuilt sort function. Next we come to dq, which is like a doubly ended queue, okay. So this is the diagram for dq if you want to keep something. So there are a lot of elements in the pipe over here, so you can, let's suppose this is the front and this is the back, so you can put elements on in the front, take out elements from the front, you can put elements at the back, you can take out elements from the back if you want to, okay. So all these things are possible, okay? So taking out from either side or inserting elements from either side, okay. Also at any particular configuration, if you want to access what is the element at some particular ith index, that's also possible in dq. So that is like order one random access. So accessing a particular ith element, if you can do that in order one, it's called random access, okay. So you have the dq of 4 5 6 and elements, you push 3 in front, so it will be 3 4 5 6. Now you push 7 at the end. Now what's the value at 2? That's this, right? This will be indexed in this form, right? 0 1 2 3 4, okay. So the 2th element is 5. Then you can pop from the front, okay, and then what is the second element? That's 6, right? So that's what the output would be, okay. So then you have q, okay. So this dq, q, stack, these are all adapters, and these are internally, so the q and stack can be internally implemented very straightforwardly using vectors. So these are all, so that's why they are called adapters, because they are based, the implementation of these are taken from the other standard sequential or associative structures. So an adapter of dq with just the pushback, just the pop front. So the pushback in the dq will become push, the pop front of dq will become pop, random access gets removed, no iterator, no range based loops, no curled braces initializer, okay. So these are the things that are there. So as you can see, this is more restrictive than dq, right? But it's a bit more faster. So that's why these adapters are created. So dq is an adapter of so the q is an adapter of dq. So these are created to optimize on dq, because dq is a heavy structure, right? It gives you a lot of operation. So if you want to use just a q, or you want to use just these functionalities, then you should be trying to use the q rather than using a dq. uh, so just as dq can be used, lists can also be used as an underlying container. So the underlying container over which the adapter can be built can be dq, can be list, right? So stack can be also an adapter of dq. So in this case we have pop, pushback becomes push, pop back becomes pop, back becomes top. So back is like what is the last element, so that becomes what is the top element, okay. random access and front removed. Okay, so random access and front are now removed. You have no iterators or range based loops. You have no curly braces. Okay, so list and vectors can be used as underlying container as well. Okay, so what are these things? Let's quickly go back and talk about the queue. So you have a queue of objects, so you can push an element from the top, and you can, so let's call this back, and this, let's call this front. You can pop elements from the front. Okay, so this is what we are maintaining over here. So you can insert element and take out the first element, or you can also see what is the element in the front. You can also, you can use that element if you want to, like without even popping. Okay, similarly for stack, the structure is something like this, that you can push an element from the top and you can take out the last element that was inserted. Okay, so there is a notion called first in first out. So whatever is inserted first gets out first. So this is first in last out, or last in first out. Okay, so this is all stack. So this is a very important generalization of the things that we're talking about. So these are the quick operations that you would be needing in most of the cases, and it's good to know what the complexities of these operations are on these things, because the vectors and deque you would be using very frequently. List is not that famous, but some problems require list as well. Okay, so random access, like can you access any I? So can you write this a of I? So for vectors and deque, yes, you can get that particular value, but in list you cannot, because it's a bidirectional linked list. Okay, push front, pop front, so on. So from the front you cannot remove elements in the vector. So vector is something like this, right? So this is like a vector, and you have elements over here, and then you can extend at the back. Okay, so you cannot remove element from the front, so it takes order n, but for both the list and deque it's order 1. Okay, pop back is order 1 for all of them. Iterators are random access in vectors and deque, but in list you can move iterators in both the directions, right? It's a bidirectional linked list. So insert and erase at an iterator. So given some iterator, if you have to remove, for vector and deque it takes order n, because if you have to remove some element that is in between, so let's suppose you have some sort of array which you have to remove an element from the middle, right, and like join them back. So doing this operation takes order n in both vector and deque, but list optimizes in this, because we know that in list you have to just change 2 pointer links and that will work. Okay, sorting in all of them takes n log n. A binary search is allowed in vectors because you have random access. Same for deque, but in list you don't have random access, so you cannot do binary search. Okay, continuous memory allocation. So when you create vectors, the memory that it gets is allocated continuously in the memory. List and deque are not created in a contiguous fashion. Okay, okay, so which one should you use, vector or deques? So both of them are quite important, but as you can see, deques are like kind of like a superset of vectors, right? So everything is better than, like, this is better than this is better than this is better than the particular this is also better, this is also same for vector and deque, this is also same, this is also same, and so on, right? And memory you don't really care about. So in some sense deque is better, right? So why not use deque all the times? So it turns out that as you have structures that are more complex, the time of normal operations get more complex as well. So if you think in terms of how they are converted to 3 address codes and run, so the functions that are implemented in these structures are complex in terms of deque than in vectors. So if you want to just use pushback, you should go with vectors, but in case you need to have some push front or pop front operation, then you can switch to deque. So try to use the STL that is just sufficient enough for the problem. Okay, that's what you should ensure. Now there is another adapter which is priority queue. Okay, so which implements a max heap. Okay, what's a heap? So it's a structure which can give you the max of elements inside it. Okay, so you can insert a x, you can find the greatest element in the set and you can remove the greatest element. So you can think in terms of like a set which you can insert some x, you can remove the max, or you can query what is the max. Okay, so this is what you can do in priority. Okay, so now to find the minimum in the heap, what you can do is insert all the numbers inside in the negative form. So what happens is you have to find the minimum out of these numbers. So if you put them in negative form, you have to now find the maximum of the negatives. So that becomes the standard task what the priority queue solves. So once you get the maximum, remove that negative that you added, and that would be your actual answer, right? The second way is to add a greater t construct. Okay, so this is available for custom comparisons. So if you define priority queue in this fashion, that priority queue of strings, which is an adapter on a vector of string and which implements this custom comparison function greater of string, if you put in things inside that, it will be in the reversed order. So it will be giving you the minimum out of everything. So the priority queue actually keeps this vector of string in a heap form such that the last element of this vector is the smallest. So greater string is like a comparator that is used even in vectors to sort it in last to small order, right? And priority queue removes the last element out of things. So that's how priority queue are actually working. Also you can do it in a way using a operator less than that you can change inside the structs, but this is not really advised. Like you are using less than symbol and it's actually meaning greater than. This becomes confusing, so it's not advised. So mostly we use the first one for quick implementation, or in case if you really need it, you can use the second one as well. Okay, so now these were all serial or adapters, right? Let's move to the associative containers that are not array based. So whatever we saw till now were something like this, that you had an array and one element was being accessed, something was removed from one end, something was inserted at one other end, something like this was happening, right? Now in associative containers, the elements are accessed based on keys and not indexes. Okay, so the type of keys is not necessarily integer but must follow a weak ordering. So you can insert anything inside a set, only thing is that the operator less than should be defined for that. Okay, now element accessed by key is order login. So in this case, whatever was order 1 of random access, it becomes an order login in this associative containers. And if you talk about the actual implementation inside the STL, they implement a height balanced balanced binary search trees called red black trees. Okay, but we're not going into the details of implementation, so we just know that STL exists, right? So let's now talk about sets. So set is like an always sorted array. So you put in values 1000, 1 2 3 4 5 40, and if you find the first element, it's 40. It's always sorted. What's the last element? 1 2 3 4 5. So it keeps these things in the sorted form. Okay, if you insert 8 and erase the last element, insert 1 2 3 4 5. If you find the if you find the first element, it's the smallest element, that is 8. If you find the last element, that's the largest element, that is 1000, because you have removed it, right? Same goes with string. You can have strings, you can have doubles inside this, right? So you can initialize the sets with unsorted sequences and it will take n log n to construct the set. But if you pass in a sorted sequence, it takes order n to build the set. Okay, so two sets x and y are considered equal if x is less than y is equal to y is less than x. Okay, equal to false. So now when you insert an element, it returns a iterator and a boolean. So iterator is the iterator to the inserted element or any existing element that already existed. So set does not allow you to keep duplicates. Okay, so set will only have one instance per key. There is a version of sets which is called multiset, which allows you to keep duplicates of the same value. But coming back to this, we have iterators to the inserted or the existing element, and there is a boolean returned as well, which is whether a new element is actually inserted inside the set or not. Okay, so if you insert 5, boolean is 1. If you insert 6, boolean is 1 because it's actually inserted. But if you again try to insert 5, it's not actually inserted, so it's 0, right? So st.size returns the size of the container. So there are 2 elements right now. Count of 5 returns how many elements are there, which are 5. So it's 1. In sets it will be 0 or 1, but in multisets it becomes the frequency of that particular element. st.erase 5 removes that particular element from the set, and again if you count it becomes 0, right? So if you want to create custom structures inside the set, so you can create a struct with having this ordering defined. This is very important, and once you define that for that struct, you can create a custom set of that particular struct objects as well. Okay, so you can insert, you can iterate, you can erase, you can count, and so on, right? So iterators inside set are bidirectional. That means if you have an iterator to some particular element, you can go to the next element, go to the previous element. You cannot directly jump in sets. Okay, so iterator plus equals to 5 does not mean that you will be taking just a order 1 to go to the plus 5 index. So it will do plus it 5 times. So if you are doing it plus n, it's actually order n. Okay, note this. So let's say you are at the first element, then you increase the iterator 2 times, so you reach this one, and then you print the value at that, it's 5. You can erase this if you want to, and this will be assigned to the next element. So when you erase, it returns the iterator to the next element that is now at that place. So iterator is now at 7. Then if you print it, it's 7. If you go back, it will go to 3 because 5 has been removed, right? We have removed this, so it will go to 3. And then if you want to find the distance of 3 to the begin, it will find out there is a difference of only one element, right? It's over here and the begin is over here, so there is a difference of only one element. Okay. So note that the distance operation between two iterators is order it2 minus it1, because in this set we know that just like this, where we discuss that it plus n takes order n, so finding the difference as well takes an order of linear type. Okay, so now set has the lower bound and upper bound also available for them, since it's maintained sorted, and this is of real interest because this is used in a lot of problem. So let's say you have a vector v. So if you want to create a set out of all the elements of a vector, this is the syntax. Okay, so set of v dot begin, v dot end. So take all the elements from v begin to v end and insert it inside the set. That's all. So since this is already sorted, this set will be created in order n. Okay, and then if you take x input and then do a lower bound in the set, you will find the first element that is greater than or equal to x, right? So if it's not end, if it's not the last element outside the set, that means there exists some element which is greater than or equal to x. You can print that, or else you will have no element, right? Everything is less than the given x value, right? Note that the syntax for lower bound over here is st dot lower bound x. It's not lower bound st begin, st end x. This is what we use in case of vectors, right? In vectors we use this syntax, but if you use this, it will be order n because we don't have random access in sets. So apart from set and a variant of that multiset, we will discuss about that later, but we also have a type called map. So maps are sometimes more useful when you have to store extra information about the key. So you can think about maps as like an dynamic array where you can keep anything inside the index and anything at the value. So you can map integers to strings and keep the particular value. So if it's not present, it creates the value. If it's already present, it updates the value. Okay, so you can like index on the strings and keep values at the string. So this comes in handy in a lot of problems. Okay, so mp.find is a function that returns an iterator to the element with key k if it exists, or else mp.end, right? So mp.find in a binary search fashion search for element of value k. Okay, now let's suppose you have a map string and double, okay, and you create two particular values. Now if you want to find jpy in this, since you have not inserted inside the price, there is no value, right? So it will be end, so this will return true, right? And if it equal to price dot find gbp, right, it's present, right? So you will have it as 0, like there will be some iterator that is not equal to end, and that iterator's first value is the key and the second value is the value. So it dot first will give you gbp and it dot second is the value, but you can also replace that value if you want to, and again if you check in the map, it has actually changed the value in that as well. Okay, so it is order 1 is allowed, but note this is very important, this part is very important, that you cannot change the first value because that will completely disorient the structure of the set that is being maintained, and that won't allow you, so the code won't allow you to do that, so and it throws compilation error, right? So for set and map there are unordered version of them. So what is unordered version? So they basically implement the same using hash table. Okay, so they have average of order one time in most of the cases, but on worst case they can take order n. So this is the thing. So in the previous one, a lot of things were taking order log n, right? Most of the things were taking order log n. So here on average cases you will need order 1, but in some worst case design you might need order n. Okay, so these are not sorted sets. So in the unordered set is not like you have a sorted elements in a sorted fashion and you cannot do binary search on them. You cannot, the begin is not even the smallest element now. Okay, also it implements separate chaining for handling collisions. So this is something specific to hash tables, we will talk about this later. And by default it also uses the mechanism similar to vector, where when the capacity fills up it doubles the size and rehashes everything. Okay, so like this is how you declare an ordered set, you insert values and you can check the bucket size. Okay, so whenever you have some particular number of element, when you are at particular I, the bucket size is generally 2 into x, like it tries to maintain 2 into x size. Okay. Now in order to use unordered set and map, the class that you are putting inside it, okay, should be hashable. So you can create custom hashes if you want to. Int, double and strings are by default hashable, but pairs are not. So if you want to create hashes for pairs, you can create a custom struct something like this and return a hash. So given a pair, what is the hash value? So let's take this simple hashing that it just takes the XOR of the two values, okay, the first and second, and that returns an integer and that is hashable. So you can create a custom hash or something like this and then put it inside the unordered set, and that will now hash these values. Okay. But note that this hash value needs to be very good, or else everything, a lot of different values can map to the same particular index, and that will actually make the time complexity worse. Okay. Now let's talk about a topic called iterator validity. So we have been using a lot of iterator, right? So st.begin, st.end, you define auto it equal to some iterator and then do plus plus minus minus and all these things, right? So in set and map, when you insert a new element, every iterator that you have is still intact. Okay, if you erase some element, iterator to the element that was erased will get invalidated, everything else will remain intact. So what I mean is that suppose you have some sorted set, okay, and you have an iterator to this particular element. Okay, you have an iterator to this particular element. Now suppose I remove this particular element out of the set, I call erase. Okay, so you have 1 2 3, the it points to the first element, but you remove first element, and then if you try to use the iterator it, it will give you wrong answers, it will give you runtime errors because this it is no longer valid because this element has been deleted, right? So the better way to do this would be this, that you have a set of 1 2 3 and you put in it equal to st dot begin, and then if you want to erase it, you assign it to the next value. So now it becomes 2, and then if you print it, it will give you 2, right? So for set and map, these are things that you need to be careful about. For unordered set and unordered map, like on insert, all iterators are invalidated if rehashing occurs, and in case of erasing, iterators are erased element, like the iterator only to the erased elements are invalidated, right? Everything else remains intact. Let's say you have something like a code with vector, and you take an iterator to the last element, and then if you delete the last element, so last few elements, and then if you try to like use the iterator, it will become invalidated, right? So these are things that you need to be careful about. So iterator pointing to end will always become invalidated after like a size change, because something got decreased or increased, so it will change, right? So these are some iterator related things that you need to be careful about before you code into things. Okay, so that's all for this session. Thank you.